1. Introduction. Thank you for the introduction, Mr. Chairman. Good afternoon, ladies and gentlemen. The topic I'd like to present today is Sustainable Road Construction, Volumetric Property Adjustments for Enhanced Performance of Recycled Asphalt Concrete. 2. Overview. This is the outline of my presentation, including 4 parts from introduction to summary and recommendations. 3. Volumetric adjustments for RAP performance. Reclaimed asphalt pavement, RAP, is increasingly used for sustainable pavements. The volumetric properties significantly affect the performance RAP mixes. Key indicators including air voids, voids filled with asphalt, VFA, voids in mineral aggregate, VMA, and film thickness can greatly impact cracking and rutting resistance. 4. Enhancing RAP mixture performance. In Taiwan, RAP storage spaces are limited, which makes it a high priority to increase the use of RAP. However, if we don't manage RAP mixtures properly, asphalt pavements may deteriorate prematurely. Controlling volumetric properties is crucial to improve RAP mix performance. Our idea is that by adding more virgin asphalt, we can improve mix performance and balance the stiffness caused by aged binders. 5. Objectives. This study has 3 main goals. First, to analyze the volumetric properties of recycled asphalt concrete. Second, to evaluate its engineering properties. And finally, to assess its performance in terms of cracking and rutting resistance. 6. Materials. We study 4 mix types: 0%, 20%, 40%, and 60% RAP. This experiment was designed to evaluate the effects of RAP content under controlled conditions. 7. Gradation curves of asphalt mixes. Here, we show the gradation curves for the asphalt mixtures. The 0% RAP group, made with virgin limestone aggregate and AC10 binder, was our control group. All of them follow a dense graded asphalt mix design. The consistent gradation allows us to clearly examine the effect of RAP content on performance. 8. Specimen designations. 8. Specimen designations. We used a naming system based on RAP content and the virgin binder added beyond optimum asphalt content, OAC. For example, 40R plus AC underscore plus 0.25 means 40% RAP and 0.25% more AC10 fresh binder than OAC. This systematic design helps us evaluate how different asphalt contents affect mix behavior. 9. Test methods. 2 key performance tests were used. The ideal CT test evaluates crack resistance and gives us the CT index. The ideal RT test measures rutting resistance and gives us the RT index. Both tests follow ASTM standards and use compacted cylindrical specimens. 10. Degree of RAP agglomeration. RAP particles tend to cluster together. After extraction, we found that fine particles agglomerate more. Because fine aggregate has a high surface area, more asphalt is required to achieve a consistent film thickness, a factor that influences the mix properties. So, clustering must be considered in the mix design. 11. Voids in wrap asphalt mixtures. Let's talk about voids. As we add more AC-10 binder, the air voids decrease, while VFA increases. VMA decreases first, then increases slightly. These changes reflect how asphalt lubricates the mix and affects compaction. 12. Film thickness of wrap asphalt mixtures. As we continue increasing binder content, we observe a steady rise in asphalt film thickness. However, at 60% wrap, the film thickness is slightly lower. This is due to more fine wrap particles in the 60% wrap mix, which have a larger surface area and require more binder to coat. 13. Load versus displacement curve, ideal CT. Here, we show the ideal CT load displacement curves. Wrap mixes display higher peak loads but also more brittle behavior. The control group, 0% wrap, has a smooth post-peak drop, which means slow crack propagation rate and good ductility. 14. Cracking Tolerance Index, CTindex. We calculated CTindex to compare cracking performance. Adding 0.25% fresh asphalt significantly boosts crack resistance. Even with 60% wrap, if we add enough new binder, CTindex can still exceed the control group. 15. Load versus displacement curve, ideal RT. In ideal RT, wrap mixes reach higher peak loads and resist rutting longer. However, they also show more brittle failure. This tells us, wrap improves rutting resistance but may reduce flexibility if not adjusted with virgin binder. 16. Rutting Tolerance Index, RTindex. This figure shows RTindex values. 60% wrap has the highest RTindex, showing excellent rutting resistance. But, as we add more fresh asphalt, RTindex decreases slightly. This is the trade-off between flexibility and stiffness. 17. Effect of air voids on RTindex. We found a strong correlation, i.e., higher air voids lead to higher RTindex. But more air voids also mean potential durability issues. So, mix design should balance RTindex and long-term performance. 18. Effect of VFA on CTindex. As VFA increases, CTindex also improves. More asphalt filling between aggregates means better crack resistance. For wrap mixes, we suggest raising VFA from the standard 75% to 85% to allow better performance. 19. Effect of film thickness on CTindex. Crack resistance improves as film thickness increases. Between 8 to 10 micrometers, CTindex reaches 100 to 150. But if thickness drops below 7 micrometers, CTindex drops significantly. So, 8 micrometers should be the minimum target. 20. Summary and recommendations. Based on the test results from this study, the following conclusions and recommendations can be made. Agglomeration plays a key role by increasing the surface area, which in turn reduces the asphalt film thickness, impacting mixture durability. The volumetric properties of RAC closely mirror those of fresh asphalt, ensuring comparable performance when properly managed. Our study shows that the ART index improves as the RAP percentage increases, indicating enhanced resistance with higher recycled content. Adding an extra 0.25% virgin asphalt significantly boosts the CT index, enhancing the mixture's cracking tolerance. We recommend adjusting the RAP VFA to a range of 65 to 80% and maintaining an asphalt film thickness of at least 8 micrometers to optimize performance. 21. End note. This concludes my presentation. Please feel free to ask any questions you may have.